Let's now look at the neural network and understand its topology. Because a neural network is actually just really simple. It's just an amalgam of different linear units that we could compose, like we did in the last section where we used a bunch of perceptrons to create the XOR. So the neural network is mostly just about the idea of the notation behind putting all of these networks together. And once we have the notation down, it's actually fairly easy to take this and to make it into an algorithm, because all you need to do is make sure that you connect the right inputs to the right output. So let's start with this, okay? We're going to start by saying we have a set of inputs x, and we're just going to lay them out as a column vector here, where we have the first input x1, x2, through xd, where d is again the dimensionality of our inputs. And we're going to have a bias just as we do as normal, and this is going to be our x0, which allows us to move our intercept around on the plane. Okay, and we're going to have a bias unit for every layer except for the last layer where we're going to create the output value. Okay, and we're going to have these layers in the middle. Okay, we have hidden layers 1 through L, which are going to be all of the middle layers here. So we have 2 hidden layers here, and our final layer L, capital L, is going to be our output. Okay, so that's written here, output layer when L equals capital L, that's the number of layers in our network. So previously we were using the logistic function, which has this nice curved shape. Again, we use this shape because it's going to compand any real valued signal from negative infinity to positive infinity and put it between a bracket, right? This bracket is between 0 and 1 for the logistic function. But just like we saw in the last part where we were calculating XOR, sometimes it's helpful to have something that ranges between 1 and -1. So we're going to substitute the logistic function for another function, a hyperbolic tangent, which goes from -1 to 1. And we're going to use this as the activation function that we're going to start with for this part of the course. Later on, when we get to deep neural networks, we're going to see a different activation function. But basically, all of our activation functions have the same idea, which is to introduce some type of nonlinearity. Why is that? Because when we compose, let's say, this input with this input together, and we don't take a nonlinearity, it would just be equivalent to a single one of these with different weights, right? Because when you add 2 lines together, you'll get a different line, but it'll still be a straight line of some sort, hyperplane. Okay, so we need the nonlinear activation function, which we'll denote as A, in order for that not to occur, so that we can get a more complex boundary as a result. So again, we talked about it being a matter of topology and notation for neural networks. So let's take a look at what this is. Now, we're going to now have a lot more weights, as we saw when we talked about generalization problems. We're going to have L layers. So we're going to denote the layers in the brackets here, where we have it in parentheses, right, as a superscript. So here we have layer 1, layer 2, and layer 3. And note that in different lectures that you'll hear from other people, if you're looking at other sources for machine learning, they may have different notation. So just make sure that you're clear about the notation that we're using in our course. So again, we have layers 1, layers 2, layer 3 for this 3-layer neural network, and the input layer is layer 0. We can think of it like that. All right? And for each layer, we're going to have a number of inputs and a number of outputs, right? Our outputs will be basically what we are having at this particular layer, right? So if we look at this layer here, layer 1, okay, it has the output coming from this activation here for cell number 1, neuron number 1, neuron 2, and neuron 3. So this one has 3 outputs, which corresponds to a dimensionality of free for this level, right? Since we have free outputs here. Its inputs come from the previous layers, and we can see what we have here, right? Our inputs are 1, 2, all the way to the nth input here, which should be actually a capital D, okay? And we have our bias, which is 1 here, okay? So we have all of these as inputs, and that will be our I, the I that we have over here, okay? So we can understand this particular index as this edge. This is a single weight, and this is the weight for layer 1, okay? For the first node in layer 1, that's the output, okay? And for the bias input, which is 0. So that's the notation that we're using here, right? This one here corresponds to this. This 0 here corresponds to this one, and this 1 means this entire layer. What about for the next one down here? What does it mean? Okay, so we can understand again, our layers are coming from the parentheses, so this is layer 2, right? This is the third input, 1, 2, and 3, so this is the third one, so that corresponds to this, and this is the 2 corresponding to the second node as output 1, 2, so this is our 2, this is our 3. Okay, so you can see what's going on here. We're going to get a theta, capital theta here, which is going to differ per layer in some cases. So for example, if we are talking about, let's say, this first layer here, this is our theta 1, okay, how many weights does this have? Well, it's going to be dependent on calculating this entire set of all of these arrows here, right? That's going to be the weight. So we're going to look at layer L-1, that means this previous input layer, okay? And we can see it has a total of 4 units here, right? And then in SL, at layer L, which is our current layer that we're looking at here, how many units do we have? We have 1, 2, 3 units here, okay? Then we're going to do 4 times 3 because our previous layer, our input layer, actually has 3 units plus our bias, right? This is our bias term. So we have 1, 2, 3 units here, and then we have our bias unit. So it's 4 times 3. There's going to be a total of 12 arrows here, right? Or 12 weights. Right, and we again using theta, but now instead of having a single value of theta, we have a matrix of values, right? 4 inputs, 3 outputs, and so we get 12 for this layer. Each layer can have a different number of weights. So for example, if we are looking at this layer here and we want to write down how many things that we have for that, this is layer 2. Then that would be simply the number of units that we have as our input. 1, 2, 3, right? 3 here, plus 1 for our inputs, times 1, 2 units as outputs, 2, and then we will have a total of 8 arrows, right? 8 weights. Which we can see because we have a fan-in of 4 and another fan-in of 4. So in the same way, we can talk about the activations for a neural network. Right? Let's concentrate first on this one here, which is the second cell of the first layer. Right? It's got an activation function that is comprised of the inputs from the previous layer, all the red arrows that we have here. So you can see they're all, in this case, noting layer 0, right, in the parentheses. Right? And since this is the second cell of the first layer, right, we're going to see that all the output variables are 2's. But because the inputs are different, in other words, the bias of 0, x1, x2, all the way in this case to x3, we're going to have different numbers for our input indices that we see here. we can ask the same question of A1 here, which is in layer 2, right? Since it's layer 2, we have a number here in parentheses that denotes 2, and it's going to be the function of the aggregate activations of all the ones in layer 1, right? All these free inputs as well as the bias term from layer 1, right? So again, we have 0, 1, 2, 3 here, which corresponds to these first input indices here, which are going in then as the blue and the purple arrows into this green node over here. So for this cell number 1 here, which we're getting our 1, all of these are going to be 1, 1, 1, 1, and 1. Okay, so we get an idea of how to annotate all the different weights and the nodes of the neural network. So let's take a look at how the network operates. Right, the network operates by looking at specific weights. Our weights we're going to call capital theta, and it's got three variables here. It's got our L, which is the number of layers, and our I and our J. So we're going to take a look at this in a little bit more detail here. We have L layers, I inputs, and let's say J outputs. Okay, and the easiest one to understand first will be our layers, right? We have capital L, which is the last layer that we're going to output, as well as layers 1 through that, which basically are all the layers of our network. So to be clear about this, our inputs of X are actually at layer 0. They're not counted as part of the network. Okay, we're only looking here at the parts that form the actual neural network, which are the ones that we want to parameterize. And after that, we can look at the outputs. Our outputs span from the first neuron at the output layer up to D of that particular layer, right? So we're going to denote that layer L. And our inputs are going to be very similar, right? They're going to be from the previous layer, so it's L minus 1, okay? But it's not going to be from index 1, right? It's going to be from index 0. And why is that? It's because this 0 indicates our bias term, right? And this bias term is going to be applied to every layer, not just the input layer, as you saw on the previous slide. All right, so what are we trying to calculate? We're actually going to try to calculate two things here. Our outputs, let's call them xj at a particular layer L, based on the inputs, right? Our inputs are going to be from a previous layer, L minus 1, right? And for each of the inputs, we're going to have an associated weight, let's call that theta, okay, of layer L, I, J, okay? So it's important to note here that this L and this L minus 1 don't match each other because our weights are associated with the output layer that we're going to look at. So this is L, and this is J and J, okay? So these two don't match, right, for the L's. Okay, and then we're going to take this and we're going to aggregate it. Right, our aggregation is going to be over all of the inputs. Those are at layer I minus 1, right, of I equals 0 from the bias term all the way to the last unit. And we're going to take all of these as a sum and apply some nonlinearity to it. So we can write that out as basically taking the nonlinearity, applying it to the signal for the LF layer, and that's going to be the same as our activation function for this layer. Okay, so that's great. We want to take a look at this particular part which we're calculating, which is our nonlinearity. And our nonlinearity is going to be, in this case, going from -1 to +1. So instead of using the logistic function, we're using the hyperbolic tangent, which has very similar properties. Again, it's going to have this nice property of simulating a hard threshold like the sine that we were doing before, right? Sine x, when we have a very negative value or a very positive value. But in the regime where it's close to 0, it's going to act more like the linear function here. It's going to act more like this green line, where it's going to be positively sloped, like the blue line here. All right, so it's going to be a nice function to choose, just like the logistic function, because it's continuous and twice differentiable, which allows us to do weight learning in the form of backpropagation that we'll get to later. But first, let's think about how we're going to do the calculations, even if we have the weights. If we have all of these thetas defined in this tensor, right, because we have 3 indices, 1, 2, and 3 here, what we're going to do is we're going to take our input and we're going to just array it as a vector. So these are all of the inputs at layer 0. Again, that's not part of our network, just our input. And we have the first component of x all the way to the df component of x, right? I'm going to take all those inputs and feed it forward to the first layer, then to the second layer of our neural network, third, fourth, fifth, all the way to our lth layer, which is going to output a single value, which is going to either be a binary outcome, right? +1 or -1 in the case of classification, or in the case of linear regression, some continuous valued output, right? So that's going to be our h of x. So that's in the case where we have a single unit. Now, in the case of when we want to do multiple classification, we're going to have multiple output units, right? Multiple output units here. So for example, in the case of iris classification, which we've seen several times, we have 3 classes, setosa, versicolor, and virginica, right? So we're going to need 3 output units here. And what we're going to do is we're going to take our instances and make them into a vector for the output. I'm going to train 3 output units like here, all right? But we're going to take each of the outputs and make it into a vector, a column vector, where the first output would be 1 and the rest -1 when it's a setosa class, and similarly versicolor and virginica. So the interesting thing is we're not training 3 separate neural networks here. We're training a single neural network where all of these weights are going to be set in a way so that all of the output units are going to try to approximate these values here. Okay? And how do we actually set the weights? That's going to be done using backpropagation, which we're going to explore. Which we're going to explore in class as well as post-class. So that's all for our pre-class lecture, so we'll see you in class soon.